All right, well, let me try the second question here that I got. And it's a little harder one. It is a magenta colored one. It's broken down into a number of pieces here. But let's just read it here. In fact, I went ahead and printed up the picture here. And they kind of help us out. They, say that we have two people here. It looks like playing catch. Ted and Mary are playing catch. And then there's some speed of an object, looks like a ball between the two of them. But then there's also this other observer, Jim, and Jim is moving relative to them, and it looks like we've got 0.6c here. Watch, it says Ted and Mary are playing a game of catch, and we put them in a S prime reference frame. Now, let me say again, as I was trying to emphasize in that other one, they're going to make it a little easier on us, although this still is a magenta problem, because they're going to tell us which one to call the S prime system. All right, so I'll call that so Ted and Mary are the S prime system. Okay, fair enough. And it is moving at a speed of 0.6c with respect to frame S, where Jim is at rest watching the action. So here's Jim, and Jim's watching these two people play catch, and they're in a moving reference frame. So I would say right there, they've just told me what V is. V is 0.6c. So remember, V is the velocity of the prime system as seen from the unprimed system. So Jim is in the unprimed system. So he's seeing Ted and Mary moving away at this speed, 0.6c. Okay? Now, goes on to then say Ted throws the ball to Mary. So this must be the ball. Throws the ball to Mary at a speed of 0.8c. Now, here's where we got to be careful. 0.8c as measured by whom? And then it says according to Ted. All right, so from Ted's point of view, this ball is moving at 0.8c. So I would say, since this is the speed of the object, so calling the ball the object as seen by the primed system, so this is the U prime, and it looks like Ted's throwing it in the negative direction, so I would say the speed is negative 0.8c as it moves in this direction. Okay, they just gave me the magnitude. Okay, and that is Ted. Now, I don't know if you want to make a big deal out of this or not, but Mary's in the same reference frame. There's no changing the perspective between Ted and Mary. They're both not moving relative to each other. They're in what we call the same relative reference frame, or in this case, inertial reference frame. So I guess I would say that Mary's seeing the same thing. Mary's seeing it, come towards her, though, in the negative direction. I mean, Ted obviously sees it go away from him, but it's still in the negative direction. And Mary, same thing. She sees it coming towards her, true, but it's going in the negative direction. So that's a U prime also. Okay, and so that's what we have. Now, they also go on to say that the distance between Ted and Mary is this huge number, 1.8 times 10 to the 12 meters. So obviously we got some big numbers. The speeds are obviously big, and the distance here is big. So not realistic. But the idea here is just can we understand these relative speeds, which we have learned why science didn't discover them. They're just something you don't normally see until you get to these huge speeds and these huge distances. All right, so the one thing I guessed then, or a couple things not given, is what speed then, maybe you might ask, would Jim be seeing this ball moving? And that would be the U. See, because Jim is in the unprimed system. So I have a feeling one of the questions are going to be asking that, if it has to do with speed. There's also probably a question here about distance. Okay, but let me just go through the question. So question A, let's move this out of the way, go, all right, so page 1, I think there might be a couple pages here. Question A, according to Mary, how fast is the ball moving? Well, I guess we kind of just answered that. That was kind of a no-brainer, but it's approaching at Mary, and our argument was, and I'll repeat it again, that Ted and Mary would see the same thing in terms of their speed. They're in the same reference frame. It would be, like you and a friend, you're each in a car moving, and you look out at the baseball. You each would say, what speed is it moving? And you would say the same thing. And if it was between you, one of you would say it's moving away from you, and the other one would say it's moving towards you. But either way, you would agree it's moving in the same direction, which is defined as the negative direction. So, all right, so that's kind of boring. Although it does say how fast, so I kind of wonder if I shouldn't put the absolute value and put 0.8 c. I mean, that's how fast it is. It sounds like it's asking for speed, not velocity. So not real sure which way the author wants the answer for that one. But I'm going to put the negative because it just seems to make the better answer, even if they only mean really speed, because they use the word how fast. All right, so let me go on to B. According to Mary, what time interval is required for the ball to reach her? Now, again, nothing real fancy here. This is just the standard formula x equals, and I'll just go all the way back to your Physics 121. That gives position and time and acceleration, and this if it's a constant acceleration. But this particular problem is not only a constant acceleration, it's a no acceleration. And all we need to do then is really just look at it from, let's see, what I say, Mary's point of view? Yeah, Mary's point of view is, okay, what is the change in position as seen by Mary, divided by the velocity as seen by Mary, would then give me the time as seen by Mary. So all of these, if I know them in relevance to Mary, there really is no relativity going on here. And I think maybe that's the point of this problem. It's going to get much harder when we start asking about what does Jim see. But if you're just asking what Mary sees, these are just straight up given. I mean, the ball goes in a distance of 1.8 times 10 to the 12th meters, and I guess technically a negative. That's the change in distance. It travels from somewhere far out towards Mary. They don't really have Mary at the origin, so this is the change in distance. But it's definitely a negative. It goes from a big number where Ted is down to a smaller number where Mary is. So technically the change in distance is a negative, which goes with our negative velocity, negative 0.6 c. And so that would be the time. And so the two negatives would cancel off, and I'd get 1.8 times 10 to the 12th, divided by a 0.8, and also divided by the speed of light, which is 3 times 10 to the 8th, and we're looking at 7,500 seconds then is how we'd see it. So again, I don't know if anything was real complicated here yet. It was just really trying to set you up and make sure you can keep track of the different observers. All right, and so these were the easy ones. These were just, what does Mary see? And Mary and Ted see the same thing. There really isn't a relativity part of this. Now, I think that changes here in C. C says, yeah, see, according to Jim, how far apart are Ted and Mary? And how fast is the ball moving? So it's a two-part problem here in C. Okay, so let's start with the first one. According to Jim, how far apart are they? Now, this is where length contraction comes into play. And this will give me a chance to say something about the proper length and the non-proper length. And so we realized in this chapter that the length of something, this is why we called it length contraction, depends on what observer is doing it. And that's a little bizarre to us. That's not quite what we thought when we thought time was absolute. And so using Newton's mechanics, this never made sense. In fact, it bothers us to even think about it at times, and mostly because this gamma factor is pretty close to 1 unless you get over 10% the speed of light, which is really fast. So the notion of saying something is smaller and bigger is kind of weird to us. But you can't really then say what the size is unless you also say who's doing the observing. So when we were dealing with speeds being relative, that wasn't a big surprise. That was even true for Newtonian mechanics. But now saying the actual size of the spaceship, or in this case, the distance between Ted and Mary, changes depending on who's doing the observer. And here's how we like to do that. Because then every observer, because you could have, Ted and Mary looking at it. You could have Jim looking at it. You could even have Captain Bob in another spaceship flying by. They're each going to say the distance between Ted and Mary are different. So you can't say the distance is without specifying as seen by whom. And that's why C is very clear. It says, according to Jim, how far apart? Okay. Now, here's how we like to handle it. Here's a diagram I like to use. I like to put a big circle and say, okay, the key one is the proper. The proper length is kind of our go-to because we could calculate what the length looks like from another observer if we know the proper one. So proper to a non-proper. Or the other way around, if we know it in a non-proper, we can return it back to a proper, okay? However, there could be multiple non-propers. Because in our case, we may have another person watching it, this Captain Bob flying by. Okay, so the real key to all these problems is to pause and say, okay, which one of these two is the proper? Or perhaps neither of them are proper. Perhaps they gave us, I better stop. But perhaps they give us like a improper length for number 1 and an improper length for number 2. And so we need to know that in order to do a calculation of what's the proper, and maybe we're asked for proper length number 3. Or maybe we are given non-proper length 1, but we're asked for a length that is non-proper 3. Okay, so what is meant by proper? Proper is kind of the... And again, I think proper is a terrible word because it makes it sound like that's the right one and all the other ones are the wrong one. But it is the hub. The proper one is the hub. And the hub is the one where there's no motion between what it is you're measuring. Okay? So, in our problem, they explicitly told us that this distance is measured from Ted. So the distance to Mary. So how far is it to Mary? Notice that Ted has no motion between Ted and Mary. So Ted would be measuring a proper length. Anybody who's moving and is measuring this length, then, like Jim, would be a non-proper. Okay? So, when they said 1.80 times 10 to the 12th meters, they told me in an indirect way that that's the proper length. So this is 1.8 times 10 to the 12th meters. That is the proper length. And since I am asked to find the speed of Jim, I'll say length as seen by Jim, that is a non-proper. So I am going to go from the proper length to a non-proper. And to do that, I have to divide by this gamma factor. Now, gamma is 1 over the square root of 1 minus v squared over c squared, where v is the velocity between these two. Now, I really want, for this problem, the reciprocal. See how it's 1 over gamma. So that would be equal to the square root of 1 minus v squared over c squared. So that's how I'm going to write it. So the length as seen by Jim would be 1.8 times 10 to the 12th multiplied by the square root of 1 minus, and so there it is. What is the speed relative between Jim and this length, which is Ted and Mary, which is the S, and that's the 0.6. That's this right here. That's where we got this. That's the 0.6 C. And of course, if you divide it by C and then square it, the C's cancel off. And 1.8 times 10 to the 12 times the square root. And I think they were nice here because 0.6 squared is 36, right? And then 1 minus a 36 is a 64. And the square root of 64, so square root, so the square root is 0.8. So it would be 1.8 times 0.8. And so that would make a distance of 1.44. So that's 80% of that. And then let me not forget the times 10 to the 12th meters. So there is the distance between them as seen by Jim. And so remember that, you know, moving objects, the phrase I like to use is moving objects shrink. And so sure enough, this length between Ted and Mary is moving relative to Jim, so Jim sees it shrink. This factor here is always less than 1. And so that's the interesting part of all this, and that's, I guess, part of C, because C had 2 parts. So let's go on here to page 2, because the other part of part C, how they phrase it here, part C says it's according to Jim, how far apart are Ted and Mary, and how fast is the ball moving? So that would be the U. You know, what is the speed of it as seen by the unprimed system? So that's the speed of Jim here. And so the formula I like to use is U equals U prime plus a V over 1 plus U prime V over C squared. Okay? And the numerator part is the classical part, the Newtonian part, the part that if you didn't have time dilation or length contraction. And so that's kind of the easier one to see, and I'll just pull this back up. I mean, if you would say something like this, you would say, okay, Mary and Ted are moving off this way at a speed of I guess I got it backwards, so let me go plus right here, 0.6 C. So that's the V. That's how fast Mary and Ted are moving. But then the ball is getting shot that way in the negative direction, so U prime is a negative 0.8 C. And if that's all we had, we would come out with a negative 0.2 c. And that would be nothing more than saying, hey, if you're going 6 this way and you throw it 8 that way, the net effect that Jim would see would be a -2. And so that's what you would get without any time dilation. Okay, but we have this extra factor down here, 1 plus, and so now we multiply these two together. So it would be -0.8 c times a 0.6 c all over c squared, which makes the c's cancel off. And so we're going to get a 1 minus, and 8 times 6 is 48, so that'd be 0.48. So that makes 0.52. And so grabbing my calculator here, I've got the -0.2 divided by 0.52. And that would then be a -0.38, and I'll just do one more decimal, 5c, going in the negative direction. So that's the speed for Jim. All right, I told you this was a pretty long problem here. Okay. And then D might be the hardest one of all, which I guess kind of makes sense. It's D. But it says, according to Jim, what time interval is required for the ball to reach Mary? Okay, now, here's where, again, according to Jim, and I'm going to play the same little trick, but use this as an opportunity to explain that when I was doing page 1, which I've lost my page 1. What am I doing? Oh, there it is. Page 1, that I did back in B, this little phrase, reduced it down to here, but just said, look, as long as you do everything, in this case, we did it from Mary's point of view, so we had the distance from Mary's point of view, we had the velocity from Mary's point of view, which gave us the time from Mary's point of view. I'm going to do the same thing, but this time it's going to be Jim's point of view. All right, so the distance traveled by Jim, and then the velocity by Jim, and the time. But here's what makes the problem, I think, magenta. Because if you look at this from Jim's perspective, okay, so I'll maybe redraw Jim here. Jim is going to see, I'll put a little T for Ted, take the ball, throw it, and it will be traveling across in the negative direction. And what we just did is we would see it going with this speed moving across. But let's keep in mind, from Jim's perspective, here's Mary. And so as the ball is traveling across, Mary is moving along. So when we talked about what distance was between Ted and Mary, back on page 1, so here is page 1C, where we did the length contraction, and we said the distance is 1.44 times 10 to the 12. That's the whole distance between Ted and Mary. And so it would be a mistake and very tempting to put that the ball traveled 1.44 times 10 to the 12th meters. The ball does not travel that far because Mary moves towards the ball. And so there's some distance here. So I like to say this, that there is a distance that the ball moves, and then there is a distance that Mary moves. Each is seen by Jim. The two together would be the 1.44 times 10 to the 12 meters. That's really the key to the problem. So I'll say it again. Easy mistake to make by putting in the distance between Ted and Mary. The problem with that is not the distance that the ball travels, because as the ball is traveling, Mary moves inward. Okay? But we could calculate these separately, and maybe I should do absolute value, because you might say final and minus initial, Mary moves positive and the ball moves negative. So let me put the absolute value. So the ball would move something like this. The ball would be the absolute value of the speed of the ball, as seen by Jim, multiplied by the time, as seen by Jim. And the distance Mary would move, as seen by Jim, would be the velocity of Mary multiplied by time. Now, maybe I shouldn't have used V's for each of those, because you might confuse that V with the V that we set up. Where'd that other page go? That this is this V. And that's not what I mean by these V's. I mean, this is the velocity of the ball as seen by, so maybe I should put here ball as seen by Jim, velocity of Mary as seen by Jim. Okay, so the velocity of the ball as seen by Jim is what we did in C here. This is the 0.385 C. Now, we got a negative, but I'm going to take the absolute value, multiplied then by time. And the velocity as seen by Jim, so the velocity of Mary as seen by Jim, that is the V. That is the speed of the S prime system. So again, notice what could go really wrong here in these problems is confusing what speed we're talking about. That's usually where students struggle with. It's like, wait, what V's are you talking about here? And so I'm trying to make that clear. This is the velocity of Mary as seen by Jim. So this is the rate at which Mary's kind of closing in as seen by Jim. So this is the 0.6 C. And actually, and I just realized now in my drawing they would be more like that, because from Mary's perspective, it's traveling faster than the ball. Anyways, but that would be times T. Now, if we add these two together, we get 0.985 C multiplied by T is 1.44 times 10 to the 12th meters. So the time is seen by Jim. Okay. And notice, by the way, I didn't do anything, that wasn't part of Physics 121 here. It's just velocity, time, and distance. But they all have to be as seen by the same person. So here's the velocity of the ball as seen by Jim and the time of Jim. Here's the velocity of Mary as seen by Jim. This would be the time as seen by Jim. And this is the total distance then traveled of the two together as seen by Jim. So now we can finish this problem by putting in our numbers. 1.44 times 10 to the 12th. Then divided by 0.985, and then divided by C, which is 3 times 10 to the 8th, and we get 4,873 seconds as the time, say this right, as the time seen by Jim. Yay! Okay. And I think that's it. Yeah, that's it. Okay, good. Hope that helped.